everyone, I'm Dr. Rizwana, working as a Professor of Physics at Institute of Aeronautical Engineering. Today in this video, we are going to discuss about energy band diagram of PN junction diode. So we are going to discuss about energy band diagram of PN junction diode. Now, already we have discussed about what exactly is a junction diode. So in order to understand its energy level diagram, first we should understand about energy level diagram of individual p-type and n-type semiconductors. So first we will try to understand energy level diagram of p-type semiconductor. Then we are going to take energy level diagram of n-type semiconductor and what is the energy level diagram once we combine p-n junction. So that we are going to see. So for that again we have to talk about impurities added, and then what happens once we add impurity, and what are the majority charge carriers, and what is the energy level which is coming into role. So here of course first I'll start with p-type, so energy level diagram of p-type and n-type semiconductors. So here energy level diagrams of p-type and n-type semiconductors. So this is the energy level diagram. So we are going to see for separately p-type and n-type semiconductors. So first I'll take p-type semiconductor, right? And what are p-type semiconductors? So here we are going to add a travelent impurity. So we are going to add travelent impurities. Okay. So I'll take a silicon crystal. To that silicon crystal I have added boron. So once I add boron, this boron, it is going to form 3 covalent bonds with the adjacent silicon atoms. And then whereas in the fourth bond position, so we can say that there is a vacancy in this fourth bond position, so it will try to accept electron. And this whole concept, if we try to explain using energy level diagram, so what we are going to observe here is, of course, this is our bottommost energy level of conduction band, which is defined by EC, and then topmost energy level of valence band, which is defined by EV. And apart from this, there is one more energy level. That energy level, it is called as acceptor energy level. So this energy level, it is called as acceptor energy level. And what is acceptor energy level? So when we talk about this acceptor energy level, so what exactly is our acceptor energy level? It is the energy level of travelent impurity. So it is the energy level of travelent impurity. Right. Suppose if you have added boron atoms, then this is the energy level of boron atom. And of course, here what we are going to observe here is first this acceptor energy level is empty. Right, and when we go for temperatures greater than 0 kelvins, but we don't go to high temperatures, we'll go to very low temperatures, then what we are going to observe here is there is a transition. So when we talk about this one, so there will be transition of electron. So here we have our acceptor energy level. So this is our acceptor energy level. And what we are going to observe here is, once we go to temperature greater than 0 Kelvin, then we have transition of electron taking place from valence band to acceptor energy level. So it takes place from valence band to acceptor energy level. Then what happens? There will be holes in acceptor energy level. So there will be holes in there will be holes in valence band of intrinsic semiconductor. And what happens to our boron or travelent impurities? They will become negatively charged because they are accepting electrons from valence band of intrinsic semiconductor. Right. So here we are going to get holes in the valence band without any electrons in the conduction band. And we know that there exists one Fermi level. So now I'm going to talk about Fermi level. So what is the Fermi level? So it is Fermi level, or it is also called as Fermi energy level. So when we talk about this Fermi energy level, so what we are going to observe here is this Fermi energy level location it is going to be different in different types of semiconductors. Also, its location, it is going to change with temperature also. And generally, this Fermi energy level, it is defined by EF. And if I try to give its definition at T is equal to 0 Kelvin, this Fermi energy level definition at T is equal to 0 Kelvin, it is uniform for all semiconductors. And how it is defined? It is defined as energy level. So it is our energy level that separates. So it is the energy level which separates filled energy states and unfilled energy states. So it separates filled energy states and unfilled energy states. Right. So, if I try to take one particular band, in that band we have different energy levels. So, these are the different energy levels. And suppose if I take this particular energy level to be EF, then below this EF, all the energy levels are occupied by electrons. Whereas above this EF, all the energy levels are empty. So we'll call it as boundary energy level, which is separating filled energy states and unfilled energy states. And this is the definition of Fermi energy level at T is equal to 0 Kelvin. Now, as you can see here is there is a role of this acceptor energy level. And what we are going to observe here is in case of our p-type semiconductors. So if we take this p-type semiconductors, here at T is equal to 0 Kelvin's location of Fermi level will be exactly middle of. So when we try to talk about the location of Fermi energy level at T is equal to 0 Kelvins in p-type semiconductor. So what is its location? EF is exactly middle of valence band and acceptor energy level. Right? And if we try to show it with the curve, as you can see here, so on x-axis we are taking temperature, on y-axis we are taking our energy levels E. So this is the topmost energy level of conduction band, which is taken as EC, and then we have this is the bottommost energy level of conduction band, which is taken as EC, and this is topmost energy level of valence band, which is taken as EV. And apart from that, I'm taking one more energy level, and this energy level, it is called as EI, which is intrinsic energy level, and which is exactly middle of conduction band and valence band, or bottommost energy level of conduction band and topmost energy level of valence band. And apart from this, if we take this p-type semiconductor, so in p-type semiconductor we have one more energy level. So what is that energy level called as? That energy level, it is called as acceptor energy level. So this is our acceptor energy level, and this is at T is equal to 0 Kelvins, and we are increasing temperature. And we know that at T is equal to 0 Kelvins, where is the Fermi level? Exactly middle of valence band and acceptor energy level. So at T is equal to 0 Kelvins, this is the location of Fermi energy level. Okay, at T is equal to 0 Kelvins, this is our Fermi energy level EF. And where is our EF? It is at the middle of valence band and acceptor energy level. And what we are going to observe here is, as temperature increases, what happens to this Fermi energy level? It starts raising towards this intrinsic Fermi level. So as temperature increases, there will be rising of Fermi level at the EF is equal to EV plus EA by 2 to the location which is EI is equal to EC plus EV by 2. This is the case of p-type semiconductor. And where is our Fermi energy level? This Fermi energy level, it will be close to valence band. This is very important point which we have to understand. So in p-type semiconductor, so this Fermi level, okay, T is equal to 0 Kelvins, it is close to valence band. So close to valence band of intrinsic semiconductor. Right? So intrinsic semiconductor. So this is about the p-type semiconductor. But when we consider n-type semiconductor, so if I take n-type semiconductor, in n-type semiconductor, so what impurities we are going to add? We are going to add pentavalent impurities. So once we add pentavalent impurities, so what we are taking? We are taking phosphorus, right? And this phosphorus, it has got 5 valence electrons. Okay, they belong to group 5. So this is the fifth electron which is free, which takes part in conduction, right? And of course the other four electrons, they are taking part in covalent bond formation. So here, as you can see, here is this fifth electron, this free electron, it will take part in conduction, and the energy level of this fifth electron, it is called as donor energy level. So energy level of this fifth electron of pentavalent impurity, so it is called as donor energy level. And where will be this donor energy level? So what we are going to observe here is, in case of N-type semiconductors. So if we take N-type semiconductors, so in N-type semiconductors, so here just we'll try to go back about this N-type. So this is our N-type, right? And when we talk about this, about its bonding, of course, of those 5 electrons, it will form 4 covalent bonds with adjacent silicon atoms. And apart from that, if we take our fifth electron, it is the fifth, of course, free electron, and its energy level, it is called as donor energy level. And if we try to draw the graph donor energy level, it will be close to conduction band, and of course this is the valence band, right? And when I go to temperatures greater than 0 Kelvin, then we have transition of electron taking place from donor energy level to conduction band. So here we'll have our donor like impurities, because they're donating electrons to conduction band of intrinsic semiconductor. So because they are losing electron, they'll become positively charged. So this pentavalent impurities, they become positively charged. And here we have our electrons in conduction band. So here we are going to get our charge carriers, okay, without any holes in the valence band. Okay, now talking about the Fermi level, so what we are going to observe here is, at T is equal to 0 kelvins, in case of N type of semiconductors, at T is equal to 0 kelvins, where is our Fermi level? Our Fermi level, it is exactly middle of, so it is exactly middle of conduction band and donor energy level. Okay, but whereas in p-type semiconductor, we have seen that Fermi level, it is exactly middle of valence band and acceptor energy level, which is closer to valence band. But in case of n-type semiconductors, where is our Fermi energy level? It is at the middle of conduction band and donor energy level, which is closer to conduction band. Now, when we talk about variation of Fermi level with the temperature, so again, I am taking temperature on x-axis, and then I am taking different energy levels on y-axis. So here we have our valence band. So this is our valence band, and of course this is our conduction band. And again we have our intrinsic semiconductor, which is middle of a conduction band and valence band. So this is our intrinsic semiconductor, which is middle of a conduction band and valence band. EC is bottommost energy level of conduction band, and EV is topmost energy level of valence band. And then we have one more energy level. What is that energy level? That energy level is donor energy level, which is energy level of fifth electron of pentavalent impurity. And at T is equal to 0 kelvins, where is our Fermi energy level? This is at the middle of donor energy level and conduction band. So this point we'll take it as EF is equal to EC plus ED by 2, right? And then what we are going to observe here is, so when we take this intrinsic Fermi level, which is middle of EC and EV, just will try to draw it perfectly at the middle of EC and EV. Then what we are going to observe here is, as temperature increases, we know that higher temperature, whether it is p-type or n-type material, it is going to behave as intrinsic manner. And for intrinsic semiconductor Fermi level, it is exactly middle of conduction band and valence band. So that's why as temperature increases in n-type semiconductor, what happens to Fermi level? Gradually it lowers towards the intrinsic Fermi level. So here lowering of Fermi level takes place. So here this is our Fermi level. And what we have to understand here is, in n-type semiconductor, here Fermi level EF, it is closer to conduction band. So it is closer to conduction band of intrinsic semiconductor. So it is closer to conduction band of intrinsic semiconductor. Okay, now I think now we got clear idea about Fermi level location in case of p-type and n-type semiconductor. Now we are going to see what happens once we So what happens once we form p-n junction? So what will be our energy level diagram we are going to see? So if we try to take out all these figures, so we are going to draw energy level diagram for p-type and n-type semiconductors. First I'll take p-type semiconductor, and then I'll take n-type semiconductor, and then we'll see how exactly we can draw this. Right, first I'm going to take p-type. So here I've taken p-type semiconductor. Okay, and I'm going to draw conduction band and valence band in p-type semiconductor. So here, so when we talk about them, this I'll call it as ECP, and this I'll call it as EVP. So what is ECP and EVP? ECP and EVP are conduction band and valence band in p-type semiconductor, right? And where is the Fermi level in p-type semiconductor? Fermi level is closer to valence band. So we have seen that in case of p-type semiconductor. So Fermi level. So also if you want, we can denote it as EFP, Fermi level in p-type semiconductors, right? Now I'm going to take n-type semiconductor. Generally, when we draw n-type semiconductor, so what we are going to do here is, here we are going to draw conduction band and valence band in n-type semiconductors lower than conduction band and valence band in p-type semiconductors. So this is the location, right? So here, as you can see, now coming to this, so this is our n-type of p-n junction. So here I'm talking about energy band diagram of p-n junction. So now we are talking about energy band diagram of p-n junction diode. So energy band diagram of p-n junction diode. Now this in n-type, how to differentiate valence band and conduction band in p-type? So this is ECN and this is EVN. And we know that in n-type, where is the Fermi level? Fermi level, it will be closer to conduction band in case of n-type semiconductors, and in p-type semiconductors it is closer to valence band. Okay, so and this Fermi level we call it as EFN. So we call it as EFN. So here ECN, EVN and EFN are conduction band, valence band and Fermi level in n-type. Okay, n part of p-n junction. In p-type, of course, ECP, EVP and EFP. These are conduction band, valence band and Fermi level in p-type of p-n junction. And when we are drawing it, generally what we'll see here is conduction band in p-type, it will be little bit higher than conduction band in n-type. Similarly, valence band in p-type, it will be little bit higher than valence band in n-type. Okay, and generally when we talk, once p-n junction is formed, we know that there is formation of depletion layer. So this depletion layer, it is denoted like this. So as you can see here, we are trying to see where is the depletion layer once we have such formation of p-n junction. So we can make out from this figure. So if you look at this graph, so here now. So as you can see here, so what exactly is this region? This region, it is called as depletion layer. So this is called as depletion layer. And once, because we have taken conduction band and valence band in N-type, so this is for PN junction. So this is energy band diagram of PN junction. Because they are lower than conduction band and valence band in P-type, what you are going to observe here is location of Fermi level in P-type and location of Fermi level in N-type, it will become uniform. And why it will become uniform? Because once we know that once PN junction is formed, the diffusion process takes place. What is diffusion process? Where we have flow of charge carriers from higher concentration to lower concentration. And because of diffusion of charge carriers, Fermi level, it will become uniform toward the PN junction. Now see here. So when we talk about Fermi level in this PN junction, so as you can see that it is uniform toward the PN junction. And one thing what we have to understand here is, in case of PN junction, Fermi level in P-type semiconductor, it is equal to Fermi level in N-type semiconductor. Simply we can take it as EF. Right? So why this Fermi level is becoming uniform toward the PN junction? Because of flow of charge carriers by the process of diffusion, where there are flow of charge carriers from higher concentration to lower concentration. And coming to P-type, we know that majority charge carriers are holes, and where these holes are present, generally these holes, they are present in the valence band of P-type semiconductor. And whereas if you go to N-type semiconductor, in N-type semiconductor, where are the charge carriers? Charge carriers, they are present in conduction band of N-type semiconductor. So these are our majority charge carriers electrons. And whereas, of course, this is N-side. Instead of saying P-type, it is better if we write it as P-side. So this will take it as P-side of PN junction. So this is our P-side of PN junction, and this is N-side of PN junction. This is P side and this is N side, and this is our holes, majority charge carriers, and this is our depletion layer. In depletion layer, we don't have any charge carriers, and as you can see, this Fermi level, it is uniform throughout the semiconductor. So this is the energy band diagram of PN junction. Okay, so if we try to look here in this particular slide, as you can see here, this is the P side of PN junction and this is N side of PN junction. And what we have done, this is conduction band and valence band in P region. This is conduction band and valence band in N region. And as we have seen here, conduction band and valence band in N region, they are a little bit lower than conduction band and valence band in N region. And of course, when we talk about P region, majority charge carriers are holes and minority charge carriers are electrons. Whereas in N region, majority charge carriers are electrons and minority charge carriers are holes. Now, diffusion takes place and this Fermi level, it will get balanced, and this is our energy level diagram. So as you can see, this is our barrier potential which is developing across the depletion layer, which is going to prevent further flow of charge carriers. So this is the energy band diagram of PN junction diode, which we have talked just now, which I have drawn in my previous case. So as you can see, this is the P region, this is our P region, and this is our N region of PN junction. As you can see, Fermi level, it is balanced throughout the PN junction, so it is common. And of course, majority are holes here, minority are electrons, and here majority are electrons and minority are holes. And of course, this is the potential or depletion layer. And there are no charge carriers in depletion layer when we don't bias our PN junction diode. Okay, so this is our PN junction diode. Now, what happens in this energy band diagram when we bias our PN junction diode? So that also we are going to discuss now. But before that, before talking about the forward biased PN junction diode and reverse biased PN junction diode, first we'll try to see what is the phenomena that is exactly taking place once PN junction is formed. Now, as you can see, valence and conduction band in N-type material, they are slightly lower than the valence band and conduction band in P-type. And we know that in P-type we have travalent impurities and in N-type we have pentavalent impurities. And these travalent impurities, what they are going to do, they are going to exert lower forces on outer shell electrons than the pentavalent impurities. And these lower forces in P-type material, what exactly we mean by lower forces. Here we talk about electron orbits becoming larger and they have greater energy compared to electron orbits in n-type materials, and because of all this process, the free electrons in the n region that occupy upper part of conduction band, in terms of their energy, they can easily diffuse across the junction and temporarily become free electrons in the lower part of the p region. So here we are talking about diffusion process. And after crossing the junction, what happens to these electrons? They will lose their energy and they'll become immobile charge carriers and they'll lose their energy to holes in the p region. And similarly, what we are going to do, of course, this process, as I told you, diffusion takes place. So depletion region begins to form and energy level of n region, of course, energy level of conduction band in n region, it decreases. And here there is one like logic to the decrease in energy level of the conduction band. The decrease in the energy level of the conduction band in n region, it is because of loss of energy of electrons to the holes in p region. So what we have seen here is, again, if we consider our p-n junction, as you can see here, in this p-n junction, we have seen that when these electrons in n region, when they migrate to p region, here we have holes. So what these electrons are going to do, they are going to lose their energy to holes in p region. And because they are going to lose their energy, so that's why what we are going to observe here is, in this case, here there will be decrease in their energy levels. But where is the conduction band? So here this conduction band, because electrons are present in the conduction band, that's why this conduction band, it is going to lower compared to conduction band in the p region. Why? Because whatever the majority charge carriers are there, which are electrons, they are going to lose their energy once they go and combine with the holes in the n region. And soon what we are going to observe here is, there are no electrons left in the n region conduction band. Okay, and as we know that alignment, when we talk about the alignment, so we are going to see that alignment of top of n region conduction band and there is bottom of p region conduction band. And once the junction comes to equilibrium value, once there is formation of barrier potential, so here what we are going to observe here is, this depletion region will act as energy hill, which is going to prevent further diffusion of charge carriers. And here, as I told you, this conduction band in n region, it is going to shift downward, and energy level of valence band also, it will also get shifted downward, and because of all this process, what happens to Fermi energy level, it will become uniform. So as I told you, when we talk about p side and n side of this p-n junction diode, as we can see here, in case of n region, there is lowering of conduction band and valence band. And why there is lowering of conduction band and valence band? This is because of diffusion of electrons from n side to p side and losing their energy to holes in n region. Now we are going to discuss about this energy band diagram. So for forward bias diode and as well as for reverse bias diode, in order to understand about this forward bias diode, I have taken light emitting diode. So what exactly is light emitting diode? If you take light emitting diode, its energy band diagram, it is represented like this, where we show two arrows going outside. So this is the symbol for LED. And so what exactly is our LED? LED will say that it's a forward biased p-n junction diode. So when we talk about this LED, it's a forward biased p-n junction diode which is made with some special type of semiconductors. So here it is made with what are those special type of semiconductors? Those special type of semiconductors, they are called as direct band gap semiconductors. So they are called as direct band gap semiconductors. And there is one more name to this direct band gap semiconductors. They are also called as compound semiconductors. So where we are going to combine different elements coming from different groups. And what is the specialty of these materials? In these materials, if I consider energy gap, and what is this energy gap? It is difference of bottommost energy level of conduction band and topmost energy level of valence band, and it is equal to h nu, which is energy of photon, or which is equal to hc by lambda. And we know that when we forward bias PN junction, if we consider our forward biased PN junction, this is P type and this is N type. So when we take this, and of course, so what is forward biasing? In forward biasing, we are going to connect P type of semiconductor to positive terminal and N type of semiconductor is connected to negative terminal. In N type, we have electrons and these holes, they get repelled and they move towards the depletion layer. Similarly, electrons in N type, they get repelled by negative terminal and they also move towards the depletion layer. And what is the process taking place? Here the process that is taking place, it is called as recombination of electron hole pair. So here we are going to get recombination of electron hole pair. And what is recombination of electron hole pair? In recombination, here our electron which is present in the conduction band, it is going to lose its energy and it is going to combine with hole in the valence band. And because our electron, it is coming from conduction band to valence band, it is going to lose energy, and that energy, it comes out in the form of photons. Why? Because here energy gap, it is equal to h nu. So that's why we are going to observe that in case of LED, our input energy is forward biasing and our output energy is light. So our LED, it will glow once we forward bias it. So that same thing when we try to show it in energy band diagram. As you can see, this is the energy band diagram of PN junction. So this is the P side of PN junction and this is N side of PN junction. And if we take P side of PN junction, this is the conduction band and valence band in P side. So this is conduction band and this is valence band in P side of PN junction, and this is conduction band and valence band in N side of PN junction. And we know that conduction band and valence band in N region, they are lower than the conduction band and valence band in P region. And here Fermi level, it is also uniform throughout the PN junction. And here majority charge carriers are electrons, and here in case of P region, majority charge carriers are holes. And as you can see, this is our depletion layer. So this is our depletion layer. First, when we don't apply any biasing, we have seen in this figure, this is unbiased PN junction. So here we have unbiased PN junction. So in unbiased PN junction, there are no charge carriers in depletion layer. But whereas once we forward bias PN junction, and here we have seen that charge carriers, they are repelled by terminals of the battery and they move towards the depletion layer. So if you observe this energy band diagram of PN junction diode, so what exactly is happening? These holes from P region, they'll come into the depletion region. Similarly, electrons which are present in the N region, they'll move towards the depletion region. Now, what is the process involved here? Process is recombination. As I told you, what is recombination? Recombination is nothing but electron coming down to valence band. So electron, so what we are going to observe here is this electron from conduction band, it will go to valence band of this conduction band of N region. Whatever electrons are present in the conduction band of N region, they'll lose their energy and they'll go to valence band of P region. And because this is just like emission, where energy is where electron is losing energy from higher energy level to lower energy level. So here energy, it has to be released, and that energy, it should be equal to energy gap. But in light emitting diode, we are making use of this special type of semiconductor. So that's why our energy, it is released in the form of photons. So here recombination is taking place. Now if we try to take similarly energy band diagram for photodiode. So what is photodiode? Which is completely opposite to light emitting diode, and our photodiode is reverse bias diode. So in this case we have taken, of course, this is for normal photodiode, and whereas this energy level diagram, it is for PIN, pin photodiode. Now what is our photodiode? So when we talk about photodiode, which is completely opposite to our LED diode. So whereas our light emitting diode, it's a forward bias diode, whereas photodiode, it is reverse bias diode. So here we have reverse bias diode. And this reverse bias diode, it is made with normal elemental semiconductors. So we make use of normal elemental semiconductors. And what are those elemental semiconductors? Silicon or germanium. So here, and what is the effect of reverse biasing? Already we have explained. So we have taken p-type here, and this is our n-type, and here p-type of p-n junction is connected to negative terminal, and n-type of p-n junction is connected to positive terminal, and of course here we have holes, and here we have electrons, and holes now they start getting attracted towards the negative terminal, and they move away from the depletion layer. Similarly, electrons in n-type, they get attracted towards the positive terminal and they move away from the depletion layer. Then what happens to width of the depletion layer? It is increased. Now, what we are going to observe here is because of what we are going to observe, whatever immobile charge carriers which are there in the depletion layer, because of their attraction towards this opposite polarity, so they'll gain energy. And what is the process involved here during reverse biasing? That process, it is called as generation of electron hole pair, and which is completely opposite to the process involved in light emitting diode. There that process, it is called as recombination. Here it is called as generation of electron hole pair. And what is generation of electron hole pair? Here first we have our electron without any energy. It means that our electron, it is present in valence band. And here we are providing energy, and that energy, it comes from our reverse biasing, okay, which is trying to uh, push it away from the depletion layer because of attraction towards the terminals of the battery. So it will gain energy and it will go to conduction band. So here, once it goes to conduction band, then we have one free electron in conduction band and there is one free hole in valence band. So here free charge carriers are generated. So here same thing we are trying to show in this energy band diagram. So this is the P side of PN junction, this is N side of PN junction, this is our depletion layer. Okay, and what we are going to observe here is, here of course it is reverse bias. So reverse bias means where a P type of PN junction, it is connected to negative terminal, and whereas N type of PN junction, it is connected to positive terminal of battery. And as you can see here, what exactly is happening, because charge carriers are moving away from depletion layer. So as you can see, these charge carriers, they are moving away from depletion layer. So whatever, see, when we talk about formation of p-n junction, in formation of p-n junction, we have taken our immobile positive ions and negative ions. So here once p-n junction is formed, and once this process of diffusion takes place, so this is p-type and this is n-type, and in the depletion layer, whatever holes are going from p-type and where they are losing their energy in n-type, they'll form immobile positive ions. Whereas from n-type, if you take our n-type, when we have electrons going to p-type, they are going to lose their energy and they are going to become immobile negative ions. So these are our immobile negative ions and these are our immobile positive ions. So what happened to these immobile positive ions? Because they are attracted towards the negative terminal of battery, so they started moving towards the negative terminal, and even this immobile negative ions, they get attracted towards this positive terminal. So because we have biased it in such a way, reverse biasing, so this is our reverse biasing. So these negative, immobile negative ions, they get attracted towards the negative bias, and whereas this immobile negative ions, they get attracted towards the positive bias. So as you can see, they are moving away. Okay, and because they are moving away, so here generation of electron, because they are moving, so they are gaining energy. So here generation of electron hole pairs takes place. So generation of electron hole pair is nothing but electron jumping. So here and here, how we are of course here reverse biasing, and what we are doing here is how we are going to make this immobile charge carriers, not only because of attraction towards their polarity. If we take our photodiode, this photodiode, it is subjected to photons. So whatever depletion layer we have, here we are exposing it to light. So once light falls on these immobile charge carriers, they are going to gain energy. So if first we have this electron in the valence band, it is going to gain energy from the photons of light which is exposed on the junction layer. They are going to gain energy and they are going to go to conduction band. So same process is taking place. So here we have our electron without energy, which is immobile negative ion. It is gaining energy and it is jumping towards the higher band. So because here what is the process involved? Generation of electron hole pair. So that's why what we are going to observe here is, so photodiode, which is a reverse bias diode, even though it is reverse bias, there is some current flowing across the reverse biased photodiode because of generation of electron hole pairs. So why here? Once we make our light fall on those immobile charge carriers which are present in the depletion layer, they are going to gain energy, and because of that energy, they are going to take part in conduction. So in this video, first individual energy band diagram of p-type semiconductors and n-type semiconductors are taken, and we have seen what is the location of Fermi energy level in p-type as well as n-type material. And then after that, we have taken energy band diagram once p-n junction is formed, and we know that once p-n junction is formed, diffusion of charge carriers takes place, and because of diffusion of charge carriers or flow of charge carriers, we'll observe that in inside of p-n junction, its conduction band and valence band, they'll become lower than conduction band and valence band in p, and because of this, what we are going to observe here is Fermi level, it is going to become uniform throughout the p-n junction. But still, even though it has become uniform toward the p-n junction, still we observe that Fermi level, it is closer to valence band in p side of p-n junction, and Fermi level is closer to conduction band in n side of p-n junction. And also apart from this, we have seen energy band diagram of forward biased p-n junction diode, also energy band diagram of forward biased photodiode. And what we are going to observe here is, when we take our diode, when it is unbiased, there are no charge carriers in depletion layer, whereas if it is forward biased, then charge carriers are penetrated into the depletion layer where recombination takes place, where energy it is going to release. And if we take special type of diodes like light emitting diodes, during forward biasing, energy is released in the form of photons. Whereas if we take reverse bias diode like photodiode, in photodiode, apart from reverse biasing it, we are going to supply energy in the form of light. Light is made to fall on the depletion layer which consists of immobile charge carriers. And what we are going to observe here is, whatever immobile charge carriers are present, they are going to gain energy from photons that are coming from the light, and they are going to go to higher, that is the conduction band, giving rise to process called as generation of electron hole pairs. So this is about the energy band diagram of junction diode in different biasing mode. So with this, I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.